All right, Chapter 7, Section 4, Properties of Special Parallelograms. So the important thing to understand here in this section is that we are still dealing with this special type of quadrilateral, namely a parallelogram. And the other important thing to understand that comes along with that is as soon as a quadrilateral is given the name of parallelogram, immediately all of the other baggage comes along with that. What do I mean by that? In sections 2 and section 3, all right, we talked about the properties of a parallelogram, namely opposite sides will be congruent to each other, opposite angles on the inside will be congruent to each other, consecutive angles in each of these parallelograms will be supplementary, they'll add up to 180 degrees, and the diagonals of each of these figures, these parallelograms, will have to bisect one another. Okay, so those things are true, as well as the fact that these are named parallelograms, opposite sides are also by definition parallel to one another. Okay, all of that baggage goes along with each of these. These are just considered the special ones. What makes them special? Well, first off, each of these figures will likely be very familiar to you, right? The one exception maybe being a rhombus. Many of us have seen a rhombus before. It's basically a square if you were to kick one of the corners and make it a little more tilted or something like that, okay? But essentially, we're going to be very familiar with these four-sided figures. Most of us, if not all of us, are very comfortable with the rectangle and the square, right? Rhombus, again, is essentially a square if you kicked in one of the sides. Okay. So what makes these special? Each of these figures has its own little special attributes. All of the other parallelogram properties still apply to each of these. It's just that now we're going to see a couple of little extra features that happen to be unique to these guys. All right, so breaking down each of these figures, it is important to note that particularly in geometry, you get a lot of layers of types of like names and titles and categories. For instance, the very broad category here is each of these are polygons. They're just many-sided figures. That's the broadest category. Okay, essentially they're shapes that have a number of sides. More specifically, they are quadrilaterals. They are each four-sided figures. And then even more specifically, they are each parallelograms. Okay, even though I did not draw the red arrows in any of these figures, these are all parallelograms. Okay, which is a specific type of quadrilateral. Not all quadrilaterals are parallelograms, but all parallelograms are quadrilaterals. And then even more specifically underneath the umbrella of parallelogram, you have these names, rhombus, rectangle, and square. The reason I go through that is in this section, a pretty common type of question is they'll give you a figure like, say, a rectangle, and then they'll give you like a little list of names and titles or categories that this might be under, and your job will be to list all the titles that would be accurate for this. And yes, it'd be very tempting to just put, yeah, this is a rectangle, done. Okay, but that's not all it is. It also is a quadrilateral. It also is a parallelogram. Okay, it's also a polygon in its most general sense. One that, and with each of these properties, I'll break these down right now, actually. First off, with the rhombus, it is a parallelogram. Okay, that's given. And it has four congruent sides. Okay, four congruent sides. Now, this is where people usually mix this up with a square, because whenever someone says like, oh, it has all four sides are congruent to each other, they immediately think of a square. And that's not wrong. That's true. A square does have four congruent sides, but so does a rhombus. Okay, the difference between a rhombus and a square, the extra thing right here is that a square is going to have four right angles. Okay, so it's like if you took a square, four congruent sides, and then kicked in one of the corners so that you didn't have 90-degree angles anymore and tilted it a little bit like this guy, then it has the definition of a rhombus. But here's again where I want to make sure that you understand this idea of categories. Technically, this is still a rhombus. This is just a very special and specific type of rhombus. Okay, because by definition, a rhombus is a parallelogram with four congruent sides. Well, a square is still a parallelogram, and it still has four congruent sides. That is still true, meaning by definition, a square is also a rhombus. But not every rhombus is also a square. A rhombus is only a square if I were to tilt this back and make it right angles into each corner. Okay, that's a very important distinction to make right there, because that tends to be one of the most confusing pieces for geometry for a lot of students. They understand that, like, okay, a square is a square, but they don't ever think as a rhombus as a possibility of also being a square. It's just if I were to tilt this back so that it was a right angle, then it would be a square. It's still a rhombus, but it's also a square at the same time. Okay. Again, one of those tricky things, people tend to like to categorize and split things up so they're completely independent of one another. Especially in geometry, it is possible for things to be multiple things at once. Okay. Another thing, a rectangle by definition is a parallelogram with 4 right angles. Okay. So many of us are okay with that piece, but it's also important to understand under that same umbrella that it is possible for a rectangle to also be a square. It's just if I were to take 2 of the sides, it's a little apparent here that these 2 sides right here are longer than its height. But if I were to shorten this up so that all 4 sides were congruent, it still would by definition be a rectangle because it'd have 4 right angles. It just would be that it would be shortened to the point where all 4 sides were also congruent. So it is possible for a specific type of rectangle to be called a square, right? Meaning that if I show you a square, it has a lot of different names I could give to this. First off, it is a polygon. It is a many-sided figure. More specifically, it is a 4-sided figure, meaning it is a quadrilateral. Under this umbrella, it is also a parallelogram because opposite sides are parallel to one another, meaning all those other properties and theorems that we talked about in previous sections apply to this square. Namely, opposite sides are congruent, opposite angles are congruent. We see that because 90-90, they're congruent to each other. And then diagonals will bisect one another. Consecutive angles will be supplementary. The 90 plus 90 will make 180 degrees. Those are supplementary. So you see all the same stuff still applying, but this is also a rhombus. Why is this a rhombus? Because all 4 sides are congruent to one another. A parallelogram with 4 congruent sides. That's true. This is also a rectangle because it's a parallelogram with 4 right angles. And then most specifically, this is what we call a square because it's all of those things at once. Okay. Again, I took some time with that because it is important to understand that there are these categories within other categories. And that tends to be one of the trickier things for students when it comes to geometry. So again, just be aware of that stuff. It is possible to have multiple names for the same thing. Okay, let's move on. So this section is exploring the properties of these 3 figures, the rhombus, rectangle, and square. Okay, so what kind of properties are we going to run into? Let's do with these one at a time. Okay, so the rhombus diagonals theorem. So immediately we're only talking about a rhombus. Now, when I talk about a rhombus, that actually also applies to a square because a square is a specific type of rhombus, but most generally, when I'm talking about a rhombus, I'm just talking about any 4-sided figure, a parallelogram with 4 congruent sides. Any parallelogram with 4 congruent sides is a rhombus. That includes a square as a type of that, but it doesn't have to be a square. So the rhombus, inside of a rhombus, if I were to draw the diagonals, so first off, going back to section 2 when we talked about the diagonals of a parallelogram, they have to bisect one another. That is still true, because it is still a parallelogram, as shown with these red arrows. But the unique thing about a rhombus, and also a square, but more generally a rhombus, is that these diagonals will intersect in a very specific way. Okay, they're still going to bisect one another. They're still going to chop each other in half. That's still true. But they're going to intersect at a right angle. They're going to be perpendicular to one another. That is only true of a rhombus, and again, a specific type of rhombus is a square. Okay, so diagonals will intersect at a right angle. They are perpendicular to one another, to use the geometric term. Okay, so diagonals of a rhombus still bisect one another, but they are what we call perpendicular bisectors because they create a right angle on the inside. That's an important piece of information. All right, next property, still about a rhombus. So I'm still talking about parallelogram with 4 congruent sides. Okay, opposite angles theorem. Okay, so first off, what we're talking about here by opposite angles, the opposite whole angle right here, this entire corner, is still going to be congruent to this bottom right corner, the whole corner down here. That is still true because it's a parallelogram and opposite angles will be congruent to one another. What is unique about a rhombus, and again, square is a type of rhombus. What is unique about a rhombus is that those diagonals that we talked about in that last theorem that intersect inside here at a right angle. So each of these four angles is 90 degrees. Okay. But what these diagonals are also going to do, unique to a rhombus, is that they're going to bisect the entire corner. What does that mean? Whatever angle measurement this entire top left corner is, this diagonal chops it in half. So for instance, if this entire top left corner was 100 degrees, each of those little pieces that was split by that diagonal would have to be 50 apiece. That is not true of all parallelograms, definitely not true of all four-sided quadrilaterals, okay? But it is unique to a rhombus. That is, these diagonals are going to bisect or split in half the opposite angles. And it's also important to understand that because opposite angles are congruent, each of those little half pieces, all four of these guys are congruent to each other because it's split perfectly in half, so they're definitely congruent to each other. But then since the whole thing has to match the opposite angle as well, each of those halves have to in turn match the other ones. Okay, we'll come back to that in our example. And then our last kind of special property specific now to rectangles is this guy down here. Now we're dealing with the diagonals of rectangles. So all three of these kind of unique special properties, these two go to rhombus, and also because a square is a type of rhombus, these also apply to squares. But this one now is specific to a rectangle, but all of them have to do with diagonals. So what's unique about the diagonals in a rectangle? They still bisect each other. That is still true because it is still a parallelogram. But what else is true about a rectangle is that not only do they bisect each other, but notice that there is a single dash on each of these guys, meaning that they bisect each other, but both diagonals in their entirety are congruent to each other. So for instance, if I were to take out a ruler and measure from this top left corner down to this bottom right corner, and it came out with, say, 7.5 inches, all right? If this diagonal was 7.5 inches, this diagonal would also have to be 7.5 inches. And because they have to bisect one another, that 7.5 inches divided by 2, or 3.25 inches, or sorry, 3.75 inches, would be each of those just portions of each diagonal. But they would all be congruent to each other. That's unique to a rectangle, a parallelogram with four right angles. Okay, so those are the theorems, the properties of special, specific types of parallelograms. Now we're going to apply it to a single exercise, a single problem here. And this is going to be pretty typical of this kind of unit, all right? You'll be shown a diagram. You'll be given a little bit of information. So down here, I'll draw this a little bit bigger on the whiteboard, okay? But we're given a single angle measurement down here in this little corner, 61 degrees. And based on that single piece of information, as well as being told what type of parallelogram I'm dealing with, in this case, a rhombus, I'll be able to find all these other missing pieces. Okay, so let's jump to the whiteboard and see what we're talking about. So we are shown a rhombus. All right, so we are shown a rhombus. What is a rhombus? A rhombus is a parallelogram. Let me stretch this out a little bit more, make it a little more emphatic. It's a parallelogram, but a parallelogram where each side is congruent to the other. So if this was, say, 5 miles, this would also be 5 miles. And then because it's a parallelogram, this segment down here has to be parallel to this guy here. So I've got to be careful about this. Not perfectly straight, but whatever. And then this one right here would have to be parallel to this one right here. And each side would have to be the same length. We'll call it 5 miles. Again, it's not perfect how I sketched it, but you get the idea. So we're told this is a rhombus. And then we are shown these diagonals. Okay. Now, again, unique to a rhombus, a parallelogram with 4 congruent sides, this intersection right here, these diagonals, because it's a parallelogram, have to bisect one another. They have to chop each other in half. But this intersection has to be perpendicular. In other words, each of these has to be a right angle. That's going to be coming in handy for the pieces that we need to find. Okay, that's one of the properties. Also, we find out that each of these diagonals has to bisect the opposite angle. So we're going to get some congruent pieces here. Now, what information are we actually given with this? We are told that this angle right here is 61 degrees. And then they give us a series of numbers of missing angles, pieces that we're trying to find. So we need to find this guy. We need to find this guy, and this guy. So again, this is pretty typical of what you're going to see throughout this section particularly, and definitely on a test hint for this chapter. And then they'll ask you some questions. They'll say like, all right, find the measurement of angle 1. Well, angle 1's right here. And my job is to figure out what angle measurement's here. So what does this have to be? This goes back to the property that we just learned, that the diagonals in a rhombus, again, the important key operative here is that this is a parallelogram with 4 congruent sides, or more specifically named a rhombus, meaning that these diagonals have to intersect perpendicularly, meaning that angle 1 here has to be 90 degrees. Why does it have to be 90 degrees? We're not asked to justify it here, but what would be the reasoning in this case? Because it's the diagonals of a rhombus. Okay. The diagonals of a rhombus have to intersect at a right angle, being 90 degrees. All right, well, measurement of angle 2 would logically come next. So the measurement of angle 2, that's its location up there. What we're going to find that is handy is the piece of information that we were given in this case. The 61 degrees here. Now, using the opposite angles of a rhombus, we know that these diagonals bisect each of these corners. So this entire corner down here in the bottom right, okay, this entire corner has to be exactly chopped in half by this diagonal I drew. So if this piece is 61, that's going to mean that this piece here is also 61. Okay. So again, this was not given. This was the only piece given right here. But because I know these diagonals have to bisect the opposing angles, that's unique to a rhombus, that's going to force this guy here to also be 61 degrees. Why is that helpful? Because this entire corner now is 122 degrees if I add these two guys together. And because it's a parallelogram, the same has to be true up in this corner, because this bottom right corner has to match this upper left corner. That's the opposite angles of a parallelogram. But now with a rhombus, each of these pieces right here, angles 2 and 3, have to also be the same measurement. They have to be congruent to one another. And we're going to find that they actually have to match both of these guys. Again, unique to a rhombus. So we actually get a little 2-for-1 right here. Right? So I can actually solve for angle 2 and angle 3 right here. They're both going to be 61 degrees. Why? Why do they both have to be 62 degrees? This goes to the opposite angles of a rhombus. What does the opposite angles of a rhombus say? That opposite angles in a rhombus have to be congruent to each other. That's actually true. This entire corner has to be congruent to this entire corner because of opposite angles of a parallelogram. But the diagonals of this rhombus have to bisect or chop in half each of those congruent angles into 2 other congruent pieces, meaning that these 2 will end up matching these 2. And it's not asked here, but these 2 down here would have to match these 2 up top here as well. We are asked about angle 4, and I'm going to get to that now in just this next piece. So now we're asked about angle 4. Angle 4 will take a little bit more work. Not much, but a little bit more work. So in order to find measurement of angle 4, it will come in handy to understand that angle 2 and 3 are going to help me here. So let me scroll back up here to my rhombus. Okay, so if I know this entire corner down here is 122 degrees, just by adding 61 and 61, angle 3 and angle 2 are also 61 apiece, meaning that that's 122 degrees. So that 122 and 122, I can actually use the interior angle sum theorem that has to do with any four-sided figure, that all of these little pieces on the outside here, okay, each of 2, 3, 4, this guy, these two, and these two up here, all of them added together have to add up to 360 degrees. That's true of any four-sided figure, parallelogram or otherwise. So what I can do is I can actually figure out what this bottom left-hand corner has to be in this figure. Here's what I mean. I could take the 122 of the bottom right corner, add it to the 122 of the top left corner, and then basically I know I have two other corners I need to find, right? And so let's say my missing piece, 2 times my missing piece is equal to 360 degrees. Let me explain that really quickly. All right, this missing piece here represents like a missing corner, this entire corner, bottom left-hand corner. Why did I put the 2 times that missing piece? Because this bottom left corner has to match the upper right corner, right? Just like these two had to match because it's a parallelogram, opposite angles have to be congruent. This bottom left corner has to match the upper right corner, meaning that I can just double that bottom left corner to find out my missing piece. All right, so if I add these two together, I get 244. And if I subtract that from 360, here's what I'm going to find. That 2 times that missing piece, let me scroll all the way down here. I need the room for the algebra. All right, 2 times that missing piece is going to equal, again, 122 plus 122 gives me 244. Subtract that from 360, and I get 116 degrees. So if I divide both sides by 2, my missing piece ends up becoming 58 degrees. All right. So what do I do with that 58 degrees? What is the significance of that missing piece, that 58 degrees? Again, using that internal angle sum. That 58 degrees tells me that that's what this entire corner has to be. This entire corner has to be 58 because if this corner is 58, that corner has to be 58. And the 58 and 58 make 116. The 116 plus the 122 plus the 122 will end up adding up to 360. So I kind of meet all the requirements necessary. But I still need to find this little sliver, that measurement of angle 4. So down here, if that entire corner is 58 degrees, if that entire corner is 58 degrees, that means that entire corner is just 2 times the measurement of angle 4. Now, where did that come from? I'm realizing I'm kind of bouncing around here. Why did I put 2 times the measurement of angle 4? Because again, angle 4 is just that little sliver. And because of the diagonals of a rhombus, it has to be perfectly split in half. So twice of measurement of angle 4 has to be that entire corner's measurement. So how do I find measurement of angle 4 specifically? That little sliver, simply cut it in half by dividing by 2. And so here's where I'll just divide 58 by 2. And I will get that measurement of angle 4 is equal to 29 degrees. Again, that's the tough one here. Took a little bit of investigative work, but 29 degrees has to be measurement angle 4. Now, just kind of confirming that, what that would mean here in this rhombus, that 29 degrees that we found here, if I were to double 29 degrees, because this diagonal has to split it directly in half, 29 times 2 would give me 58 degrees for this entire corner. That 58 degrees plus its double over here would give me 116. That 116 plus the 122 plus the 122 would get me back to 360 degree internal angle sum for any four-sided figure, let alone a parallelogram. So anyway, that's the kind of thing that you can expect here in this kind of section where you're like given limited information and you're going to be asked to find missing pieces to those angles. You can see that fully worked out in the solution sheet as well on Google Classroom if you need a little bit more help, but I'll go ahead and stop recording there to end section